Welcome to today's Explainer. Look, we live in a world that is absolutely swimming in satellite imagery and artificial intelligence. Every single day, algorithms are scanning the Earth, churning out maps of forests, oceans, urban sprawl, you name it. But here is the million-dollar question. How do we actually know if the computer got it right? Well, today we're going to demystify the ultimate lie detector of remote sensing, the error matrix. It's a remarkably simple question, but man, it is the one that keeps geospatial analysts wide awake at night. You see, just because an algorithm beautifully colors in a map, labeling one patch green for forest and another gray for urban, doesn't mean it's actually reflecting reality. Algorithms get confused. They mistake wet sand for water or a green roof for a dense tree canopy. To evaluate these AI-generated maps, we literally cannot just trust our eyes. We need a rigorous mathematical way to measure classification accuracy. We need a tool that compares the algorithm's guesses against verified ground truth. So here is our roadmap for the explainer today. First, trusting the algorithm's map. Second, building the error matrix. Third, the overall accuracy illusion. Fourth, omission and commission errors. And finally, beating random chance with kappa. All right, let's jump right into part one, trusting the algorithm's map. Before we can even begin to grade an algorithm, we need the answer key, right? We do this by collecting known ground reference data, which is often just called ground truth. Now, landscapes change fast. A forest today could literally be a cleared construction site tomorrow, so it's absolutely crucial to collect this reference data as close to the image acquisition date as possible. But how much data do you actually need? Well, in remote sensing, 50 is your magic number. It's highly recommended to collect a minimum of 50 sample pixels per land cover class. So that's 50 confirmed pixels of water, 50 of sand, 50 of forest. You get the idea. And if you're dealing with a massive study area or a super complex landscape with tons of classes, you really need to bump that up to 75 to 100 samples per class just to ensure your stats are valid. Now, here's a critical rule that so many beginners get completely wrong. You absolutely cannot test an algorithm on the exact same data you use to train it. Think about it like a student studying for an exam. If you give that student the exact same practice questions on the final test, of course they're going to get a perfect score. But you haven't actually proven they understand the subject. To get a true, honest measure of real-world accuracy, we have to use a strictly independent validation dataset. This testing data is withheld entirely while the algorithm is learning, which brings us to step two, building the error matrix. Once we have our independent testing data and our algorithm has spit out its classified map, we bring them together. We do this by building an error matrix. Sometimes you'll hear it called a confusion matrix or a contingency table. And what's brilliant about this is how it organizes chaos. Instead of staring at a massive, messy map, it takes all those thousands of data points and lays them out in a neat grid. By comparing the relationship between our known ground reference data and the corresponding results produced by the algorithm, we can quantify exactly where the model succeeded and exactly where it got confused. Let's break down the structure. It's actually pretty simple. By convention, the rows represent the map, so the classification results from our algorithm. The columns represent reality, the ground reference data. If you follow a row and column of the same name, say water and water, they meet in the diagonal. Any numbers on that diagonal? That's a perfect match. The algorithm nailed it. Any numbers falling outside that diagonal, in the off-diagonal cells, those are your errors. Moving right along to part three, the overall accuracy illusion. So, from the raw counts on that grid, we calculate a few specific statistical measures. The first one, and for sure the most common metric you'll see in any report, is overall accuracy. It's super easy to calculate. You literally just add up all the perfectly correct pixels falling along the diagonal and divide that by the total number of reference pixels. It gives you this wonderfully quick snapshot of success. You can proudly say, my map is 85% accurate. But, warning, this single number comes with a massive blind spot. It does not tell you anything about how well individual classes actually performed. The crucial point to remember is this: an 85% overall accuracy sounds fantastic, until you stop to think about the physical reality of that remaining 15%. If you're mapping a 100-hectare area, 15 hectares of your map are completely, entirely wrong. And this gets really dangerous if your map has unbalanced classes. Say you have tons of easily identifiable forest, but just a tiny ecologically vital sliver of wetlands. Your algorithm might ace the forest classification, completely bomb the wetlands, and still walk away boasting an 85% overall accuracy. To see those hidden flaws, we head to part 4, omission and commission errors. To get the real story, we have to look past the overall percentage and examine that matrix row by row and column by column. We're looking at two distinct types of failures here. First, an error of omission, also known as exclusion. This means the algorithm mistakenly left a true pixel out of its proper class. It looked right at a real tree and failed to map it as a forest. We measure our success against this using what's called producer's accuracy. On the flip side, we have errors of commission, or inclusion. This means the algorithm incorrectly shoved a foreign pixel into your target class. It looked at a green roof and mistakenly labeled it as a tree. We measure our success against this using user's accuracy. When you actually compare these metrics class by class, it's fascinating because producers and users' accuracy are almost never the exact same. Take the water class on this table. The producer's accuracy is a flawless 100%. That means every single pixel of actual water on the ground was successfully found by the algorithm. Boom! But look at the user's accuracy for water. It's only 93%. Why? Because the algorithm committed an error of commission. It took 12 pixels that were actually sand and incorrectly tossed them into the water bucket. And this brilliantly captures the two very different ways we interact with map data in the real world. The map maker, the producer, cares about omission. They're asking, out of all the real forests that exist out there, did my algorithm successfully find and map all of it? But the explorer, the end user, they care about commission. They're asking, if I trust this map and I hike out to this specific spot labeled forest, what is the probability that I'll actually find trees rather than a misclassified parking lot? Both perspectives are absolutely essential, and the error matrix gives us both. All right, part 5, beating random chance with kappa. So even with all these accuracy metrics, a real skeptic might throw a curveball and ask, what if the algorithm just guessed randomly? Seriously, if I blindfolded you, handed you a bucket of pixels, and told you to just throw them at a map, sheer statistical probability says that some of those pixels would accidentally land in the right category. So how do we mathematically prove that our AI model actually learned something, instead of just getting incredibly lucky? Enter the kappa coefficient. To compensate for that chance agreement, analysts use discrete multivariate statistics. Looking at the formula here, it essentially takes your observed overall accuracy, subtracts the expected random chance agreement, and scales the result. It strips away the dumb luck factor to give us a true measure of performance. Put simply, kappa proves how much better your classification performed compared to a totally blind random assignment of pixels. A kappa value of 1 means you have perfect agreement with reality. A value near 0, yeah, your expensive AI algorithm basically performed no better than a coin flip. Let's anchor that math into a concrete example. Say your analysis yields a kappa value of 0.80. That implies your classification process successfully avoided 80% of the errors that a completely random classification would have produced. It is the definitive proof that your map is reliable beyond mere chance. And that brings us to our final section, the map's final verdict. Whether you're using a supervised method that heavily relies on training data or an unsupervised method that clusters pixels automatically on its own, the error matrix is the essential tool that anchors our digital maps to physical reality, which leaves us with this final thought. Next time you look at a beautifully colored satellite map in the news, remember, an 85% accuracy means 15% is wrong. Does that matter? Well, if that 15% is just misclassifying some empty dirt fields, maybe not. But if that 15% is misclassifying rising floodwaters or dying crops, it changes everything. True accuracy isn't just about celebrating a high overall percentage. It's about knowing exactly where, why, and how our algorithms fail. Thanks for joining me on this explainer, and always keep questioning the map.